Okay, if you're staying for this session, if you could slowly make your way to the seating area. Thank you. All right, so welcome to this two-part serious talk. We're going to be covering the current generation of Spring MVC 4.x. What are the new features in 4.3? We'll do a quick survey of that. And then we're going to move on to Spring 5 and the reactive programming topic, which tends to generate a lot of interest because it's a new way of looking at things. Actually, in the second half of this first part, I will be already introducing talking about reactive programming, and then in the second talk we're going to continue with that subject and also look at Spring 5 and how it relates in Spring 5. You got a little bit of a preview in the overview that Jürgen gave, but here we're going to go into a lot more detail, and we're going to get a lot more context about why this is important and when it applies. So let's start with Spring MVC 4.3 first, and then we move on to the reactive programming part. So what are some of the new features that we have in Spring MVC? In 4.3, specifically the features, a lot of the features that we're talking about here. So first of all, probably all of you know the request mapping annotation. But how many of you know that in 4.2 we introduced the possibility to do your own composed annotations, which means that instead of the request mapping annotation, you can create a custom annotation like, post JSON or, get JSON, and then you can annotate that with the request mapping. And basically, it's a very easy, very quick way to create your own custom request mapping annotations if you have certain kinds of things that you do in mappings very commonly. So we did that in 4.2, and then we immediately began thinking, wow, this is nice, so should we actually create some kind of custom annotations ourselves that we can put in the framework that everybody can make use of? And as we thought about it, we came up with some ideas. Interestingly, first of all, we knew from the beginning that we wanted to keep it relatively simple because we don't want a whole bunch of flavors of these annotations to be in the framework itself. I'm sure they will haunt us in articles for years to come. We see all kinds of different variations. It's fine for applications to do that. But obviously in the framework we have to be a little bit more careful. So basically we wanted to stick to something that is very, very common and very widely used, and we didn't want to create a lot of confusion. But one thing that caught me a little bit by surprise is how much debate it generated within the Spring team, with some favoring the very short version of @get, @post, @put, @delete, and others more on the side of what you see here, which is eventually what we settled on. So there were different kinds of camps there for brevity versus consistency. But ultimately, I think the thing which matters the most, and even this I will show you saves quite a bit. Like if you look at, this is how you might express a request mapping annotation without these composed annotations. And then you see that the end result here, get mapping, is much shorter. And I should say that there was a third camp of people who basically said you shouldn't do this at all. And the reason why they said that is because they thought that it would introduce a lot of confusion, that you would have two different options. When do I use this? When do I use that? And I think probably the most important argument, prevailing argument for introducing this annotation is that the request mapping annotation arguably is too general for the most common case. In other words, in most methods, you actually should express what the HTTP method is. And in order to do that, as you can see, you end up with a rather long annotation declaration there. And for that reason alone, in order to make the right thing easy, we introduce these annotations. Sure, get mapping is a little bit longer, but it's more along the lines of request mapping. And the other thing that we decided to do was to keep the number of attributes exactly the same. So you can really think of this as a shortcut for the request mapping annotation without any other differences. It's literally just syntactic a shortcut where you don't have to spell it out the way you used to before. So it should be easy mentally to think about. It's just the preferred way. There's no reason not to do it this way. If your method has to handle a single HTTP method, which is usually the case, this is the way that you should do it. And it's much nicer and it's much easier to do it. Keep in mind, though, that you will still need the request mapping annotation. For example, if you want to express something at the type level. Obviously, at the type level, it doesn't make any sense to narrow things down to a specific HTTP method in most cases. So if you want to express some kind of a URL prefix shared across every method in the controller, then this is the way that you would do it. And then we did the same thing for another set of annotations. So now we have also request scope, session scope, and application scope. And if you were to go and drill into those annotations to look at them, you will see that they're themselves annotated. This is where we're coming from. So you might, for those of you who might be using scoped beans, let's say you want to declare a bean that should be stored in the session and kind of follow the life cycle of the session or the request. This is how you might declare such a class and then access it, inject it into your controller. But you can see here that add session scope is a nicer way to do it. So these were just obvious things that we did once we had the ability to compose annotations. And again, remember that you can create your own annotations if there are scenarios for which that works. And it's very easy to follow the example. Just look inside how these annotations themselves are declared. And you can create additional attributes, and you can put an alias on each attribute to say what attribute it maps to. So you can even rename basically some of the you can really create your own custom annotations with just a few lines of code. Very, very simple to do. We have a couple of other new annotations, request attribute and session attribute. They are very simply about getting access to request or session attributes from a controller method. So this is, for example, what you might do. You might declare something that looks like this, and it's a shortcut for taking the request and then saying get attribute on the request. It's really as simple as that, nothing more here going on. It's just plain access. Same thing for session attribute. Oops. Right. So the same thing is true for session attribute as well. But just remember that we also have another annotation called session attributes, which is one reason why we've hesitated in the past to add these annotations. Session attributes, for those of you who may not have seen it, actually has a slightly different purpose. It's more to do with when you're working with attributes in the model and you want them to survive another request. Let's say you're doing a form and you're first loading the form with some object from the database, and then you want to allow the user to enter in the form, and then when they post back, that's 2 HTTP requests, and you want the object to be stored in the session in between, and then so basically when you put something in the model, you can put session attributes at the controller level to say, if you see such an attribute in the model, put it in the session until I say that I'm done with it. And then there's actually a session status that you can take into your controller method and say, now I'm done. So whatever is referenced by that session attributes, you can clean it. So it's a way to basically keep something in the session for a certain amount of time while the controller is doing something. So it's a different sort of thing, and we didn't want to mix those two use cases, which is why we introduced those other annotations as a separate mechanism. Anybody using controller advice? Familiar with controller advice? Okay, I see a few hands. So it's a kind of a natural thing to understand if you think about exception handler methods, the annotated exception handler methods. Typically those you will put in a controller and then deal with the exceptions in the controller. but how do you make global exception handler methods that apply to all controllers? Same kind of style, but they should apply to all controllers. And the way to do that is to basically, instead of a controller, you declare controller advice, and then anything you put in there, like model attribute, exception handler, or init binder methods, apply to all controllers. And there's a way that you can actually say which controllers, what packages. There are more fine-grained mechanisms to control that. Now, we also have a REST controller advice, which is basically similar to REST controller. When you have an exception handler method, you don't have to say response body. It's just automatically assumed that it's for rendering to the body of the response. We now have a binding attribute on the model attribute, and that allows you to say that binding should not happen. Here is an example of that. So here we have a model attribute method which is going to be invoked before the request mapping method, or in this case a post mapping. And it's going to load an object into the model. Now what happens then is that when you refer to that model attribute in your actual request handling method, like the update in this case, typically what we do on a post is we mapped the values from the request onto that object. We bind, that's what we call data binding. And that's kind of happens automatically, but there are situations in which that's not actually what you want. Like here, the foo object is not what you want to bind to the request. That's just something that you preloaded. But separately, you have a foo form, an object that represents the form data that's coming from the browser. That's what's going to be automatically bound to the request. So there is a way now to basically say don't do any binding. Right, HTTP options, HTTP head, automated handling for that. So these are things that we should have supported a long time ago, but for one reason or another, now is the time where we're actually putting support for that, because Spring MVC is actually in a very good position to provide automatic support for both of these HTTP methods. So for example, with HTTP options, what should happen is that when you make a request for a particular URL, the server is supposed to respond with something that tells you which HTTP methods are supported at that URL. It's a kind of discovery mechanism that clients can use. And what happens if you don't do anything by default is that the base servlet, which the dispatcher servlet extends from, the HTTP servlet, will list all HTTP methods. So it's basically saying, I don't know, so I'm going to tell you that I support all methods, all HTTP methods. So not ideal. It gives some response. There is some implementation, but it's not ideal. So we are actually in a good position in Spring MVC because we know exactly what methods are mapped to which, what controller methods are mapped to which HTTP methods. And this is, in fact, what we do now in 4.3. If you make a request like shown here, we, in its HTTP options, now you can explicitly map your controller method to HTTP options. You can handle it. But if the method remains unhandled, we actually check to see, is that URL matched by any controller methods? And if it is, then we say, okay, which HTTP methods are supported based on the mappings? And then out of that, we generate automatically a response. So it's kind of a second line of defense. You know, first we see, are you going to handle the HTTP options? And if you don't, then we figure out, oh, but this is HTTP options. Let's try and figure out now, can we generate a proper response? So you can see here that we're responding with the allow response header, which lists that, in this case, we're supporting get. But we're also listing head, because now we're automatically supporting head. That's an implicit HTTP method that we support automatically, which I'll talk about now. So what happens with head, or what should happen, is that when the request comes in, it should work exactly like get minus the body. So you should get exactly the same response headers, so the client can see what response headers you would get, but without any content in the body. And you can see that in action here. a sample response from a controller method. So as you can see here, you don't have to actually explicitly do anything. Now we automatically attach this kind of support. Now, once again, the HTTP servlet, the base class for the dispatcher servlet, does and always has automatically wrapped the response. And if it is HTTP head, they kind of ignore any writing to the body. So the base HTTP servlet always handle this correctly. But the thing is that if you're explicitly mapping your method to get, our own request mappings aren't going to match for head. So this was a relatively trivial fix on our side to basically say, if you have get, that also means you support head as well. So that was a very trivial fix, and then after that, everything just works. Essentially, the method gets invoked, it does what it does, but the body gets ignored, and the client gets only response headers. Forwarded header filter. How many of you are familiar actually with the URI components builder? Has anybody used URI components builder? Okay, I see a hand or two. Or better yet, there's an MVC URI components builder. So these are very, very cool classes that allow you to build links. So for example, if you're in a controller method and you want to reference another controller method and you want to create a link, you could embed the actual link. Or there's a cool mechanism where you can actually refer to that controller method, a bit like when you're using mock frameworks and you actually are invoking an interface, but it's not the actual component being invoked. So there's a very nice way to build links to other controllers without hard coding the request mappings. So take a look at MVC URI components builder for that. Now, we've always supported X-forwarded headers. If you've probably come across this, but if you haven't, if you don't know what forwarded headers are, this is essentially when there is a proxy. The proxy may decide to change the URL, and it may switch the protocol from HTTPS to HTTP. It may change the host as it forwards to the next phase. A firewall might do that at any point along the way. So what happens is that they put a header, if they make such a change, that allows you to know what was the original URL that the client would have seen. And again, this is important because if you're building links like using the MVC URI components builder, you actually want to build a link that's going to work on the client side. You know, the client should be able to see the original host so the request will work. So we've always supported the X-forwarded headers. We automatically detect them in the URI components builder. But now we also have a forwarded header filter, which means that you can install that in the beginning of your request processing, and that will wrap the request. And now automatically all you see is just the original host, the original whatever methods you use in the HTTP servlet request. That will give you the information that matches to the original client information the client sees. And that makes things a little bit more reliable as opposed to when you deal with the URI components builder, because that's a specific place where we support it. But if you use the filter, it's going to work everywhere because anything that's using the HTTP servlet request is going to see the correct information from a client perspective. So you just add this filter and it should just work. We have a couple of improvements on the client side as well. For the REST templates, of course in 4.2 we added additional HTTP clients. We now support OK HTTP. We support Netty as the client internally. But one little feature that's worth noting here is the ability to customize the URI template mechanism. So as you know, typically you provide a URI template as a string, and then you can add some variables, and then we kind of merge those and create a URL. Over time, there have been like different things, like for example, how the encoding happens of those URI variables, or they have been tricky situations like that, or even there's now an RFC with advanced syntax for URI templates, right? There's some fancy ways to build URI templates, but it's very, very different from the way we've always done URI templates. Our mechanism is somewhat straightforward and simple, but it works, and we don't want to really kind of pull the carpet on everyone. So we've created this mechanism that allows you to completely replace, even if you want the URI template mechanism. But in this case, I'm showing you an example of customizing it a little bit. So if you, for example, don't want to always specify, you have some variables that you always specify with every URL. Instead of repeating that everywhere, you can simply provide a map of default URI variable values and set that on the REST template. And then, as you can see at the bottom, all you have to specify now is the ID. You don't have to repeat the host, and you don't have to. Very simple idea. But again, the more important thing here is that if you look in the REST template, there are other methods that allow you to completely customize the URI template mechanism, or even use a different library for it. And also, anyone using the client-side mock REST testing? It's a neat feature, okay? Definitely check that out. Here is an example. We did some improvements there as well, but this will give you an idea of what it is. So if you are using the REST template and doing some client-side HTTP requests, making requests, then you probably have code that actually relies on using the REST template. So how do you test this code? This is here an example of where we can mock out the server, and we can specify what the responses should be to specific requests. So that way, as you test your client-side code, it's not really hitting any server. It's just giving pre-canned or canned responses back to you. So you can see here we're creating a REST template. Then we're creating a mock REST service server, and we're binding the REST template to that server, which basically injects a custom request factory. But this is the syntax basically for doing that, and then you can declare that a request to a particular URL should respond in a specific way. So you can basically like literally provide all the responses that should be given back to the client. What we did in 4.3 is that we made that less strict and more flexible. So you can specify how many times a particular request should be expected, and also should they come in a specific, should we stick to the declaration order, or should we ignore, can the request come in any order? So these are nice improvements that will probably look familiar from other testing frameworks. So definitely if you're using the REST template, this is well worth checking out and using. It's very similar and complementary to the mock MVC, which I'm guessing more people are using for server-side testing. All right, let's see how we're doing. Okay, so we're going to start on the second part for reactive programming. Any questions on anything so far? Straightforward enough. For the three features. One, is that a question? Yes. Okay. I didn't hear the first part. I just heard JAX-RS. Is it interoperable with JAX-RS? Are you talking about the client side or Spring MVC in general? Okay. Spring MVC in general. So Spring MVC and JAX-RS have been around both now for a long time. I think JAX-RS goes back to, 2008 maybe. I don't recall exactly. Spring MVC longer than that. So basically, Spring MVC dates back to the beginning of Spring. If you go back to some of the earliest classes from 2003, they are related to Spring MVC, so that's where it all starts. And interestingly, with the reactive topic, we're actually also starting on the website, because that's a lot of things start from there. You need that first. So by the time the JAX-RS came around and the whole REST versus SOAP debate, we already had some pretty established ways and defaults. So while JAX-RS does things in ways that are in some ways similar and comparable to Spring MVC, we really see them as alternatives. We had an opportunity to actually do things the JAX-RS way or not. And it would have been kind of pulling the rug on the existing Spring MVC defaults and many subtle things which, we provide an experience for users that's alternative to basically to what JAX-RS provides. So you can think of them as two separate options, two alternatives to each other. It's a bit similar to like if anybody's into JSF, you have Tapestry. You can go with JSF or some JSF frameworks, or you can go with Tapestry. It's the same kind of idea. It's a choice. You can use what is considered to be the standard, or you can choose another framework. Another question? Yeah.
So like let's say some of the clients actually where the backend server doesn't change a lot because they mostly build the legacy on backend systems they get financial data or whatnot and display the front end.
Mm-hmm.
What are the motivations for those clients who want to upgrade from 4.x to 5.0?
Okay, so we're going to get to the 5.0 topic. The question is, what are the motivations for upgrading? There's certainly a lot happening. And actually, back to the JAX-RS question, the reactive topic is now something that gives us a lot of leverage that we can move ahead. Java 1 was just last week, and they talked about the plans for JAX-RS. And one of the things is that I'm really not sure they're going to get to the reactive topic very properly. So again, it's different ecosystems and it's different evolutions. One more, and then we'll continue.
Just a general kind of spring question.
Yep.
There's no plans to phase out XML configuration, is there?
To phase out XML configuration? No plans to phase out XML configuration. It's really in the Spring is not biased to any particular form of configuration. Spring Boot is. But the Spring Framework is not. The Spring Framework is built to work as different options have appeared over time, like when annotations came in Java 5, then came Java config side by side with XML. It tends to be the preferred way of doing things nowadays with Spring Boot. But we're not phasing out XML configuration. In fact, you will see new options now with the whole Lambda style functional direction with Java 8. And the baseline for Java 8 in Spring 5. Okay, so let's move on to the next topic, and then I'm sure that will generate even more questions, so we can have time for that. So what we'll do is in the next 15 minutes or so is we'll get started on introducing this topic, and then we'll continue on that in the next slide. So I'm going to actually provide much more context and emphasize much more on the why we're doing this, where we're coming from. And we started working on this topic about 2 years ago in the Spring Framework when we first began thinking about what is now becoming Spring 5 and the reactive theme. And thinking back, kind of relating in my own experience, if anybody remembers, back to Java 5 and around the days of 2006 or so is when this book from Brian Getz came out. And of course, he's one of the JDK architects, very much involved in the concurrency as well. And Java 5 gave us some very strong concurrency improvements a long time ago. But when this book came out, it had some interesting ideas. It talked about the fact that where now computers are not getting faster, Moore's law is not giving us benefits automatically. We're not getting a free lunch from the hardware, but we're getting more CPUs, we're getting more cores within a CPU, and our applications need to become more concurrent. And I would say that since then, actually applications are also more distributed very commonly, which means that they need to be even more capable of dealing with concurrency as well as latency. If you're making a call and that call is going to block, you're actually using a lot of resources if you're waiting for that, if that's happening a lot in your application. So he basically said some things in that book. Also, he talked about how to deal eventually. I mean, we got thread pools in Java 5, and that's kind of like the path to asynchronicity in Java. We got some other cool types, but he also talked about strategies for backing off, pushing back the load. And certainly the thread pools in Java, they allow you to have a queue. There's different strategies for what should happen if the queue is full and you can't take any more requests. But ultimately, it's all within thread pool, right? A thread pool is a way of achieving a little bit of asynchronicity on top of blocking calls to make them look asynchronous. But ultimately, that's not a strategy throughout your whole application. And if you really start to do this a lot, it gets out of hand. And that's how 2 years ago we came to this topic, is because some of the large companies like LinkedIn began to publicly talk about the fact that the kinds of things that they do, there aren't off-the-shelf solutions, and the way they have to scale and deal with so many requests means that there's so many thread pools all over, and it's very difficult to manage, and it's very expensive to maintain a lot of concurrent connections. So that's the general topic, and Brian Getz in the book, I recall at the time, it made kind of a prediction that we will have to change our ways, and I remember thinking at the time, well, that really, I really get what he's saying, but what does that really mean for us in Java, right? What is going to change? The Java 5 provides thread pools, okay, so we can use that. So it wasn't very clear to me. And it wasn't until, well, of course, if we fast forward 10 years, now also we do very different kinds of applications. So you can argue that even though not everybody is doing this, not everybody is writing cloud applications, this is now something we aspire to. This is something that has become very important, and these are the kinds of problems that we want to solve. It's no longer the SOA from a number of years ago where we kind of thought it was a good idea, but in practice, there wasn't enough. Now there's actually enough impetus to try and solve and tackle these issues. Also, in those 10 years, other things happen outside of the Java, ecosystem. So you have Node.js in 2009, and I remember that and thinking, well, how is JavaScript going to run on the server side with a single thread? And they came up with the whole non-blocking, approach, and using a single thread to service a very large number of requests. It's kind of interesting that it took a single-threaded platform to demonstrate to us, the JVM guys, what you can do with a single thread. And it makes a lot of sense, actually, if you think about it, because they're naturally constrained. They have no choice. They had to invent this mechanism, or there is no other way. If you block that one single thread, your server is out. So they invented the whole kind of non-blocking all the way programming model. Everything becomes asynchronous. Nothing can ever block. And they showed how you can scale vertically, and you can make the most of your process with a single thread. And again, I looked at it and I thought, wow, that's very cool. But it's not easy to replicate that in Java, because in Java we have a lot of momentum. We have a lot of existing libraries that are blocking. We can't just they started from scratch and they did something that was a great idea, but it takes much longer for this to happen in other areas. Of course, in Java, we're now, again, at a point where these things really matter and those ideas have been around, so that's really what's happening here. So the impact on the programming model, kind of the big picture of things, is that writing imperative logic, which was always the simple way to do things, and when I say imperative logic, I'll show examples in a moment, I mean the way we write logic, right? You call something, when that thing comes back, then you do the next thing, you lay out your algorithm like that, and if that thing is going to block, well, then you wait until it gives you back a result. And the servlet container puts every request in its own thread, and so that gives us a very simple model to use for programming. We just take that thread and do everything we need to do, and then we return. But even that is no longer simple in cases where we're forced to deal with asynchronicity. The more we do things like calling out other microservices or calling things that can take time, we are compelled to use asynchronous libraries, and those libraries have callbacks, and then we have to deal with those callbacks, and you have to do a lot of that. You're already dealing with problems that you're not well equipped to solve. That's, you're not on a foundation on which to deal with these problems. It's kind of an afterthought. And also there are limits of scale with imperative logic. I mean, you can go very far, but again, if you're doing a lot of non-blocking I/O, that's going to start to use up resources, and it becomes expensive. So we talk about becoming fundamentally asynchronous, kind of taking a very different approach here, a bit like Node.js, But of course, in Java, we don't have to be limited to a single thread. We can afford more than one thread. But the point is that we're talking about a very small number, limited number of threads, typically trying to follow the number of cores because that's how many things you can actually do at the same time. And that allows us to scale more efficiently, but of course it has quite a few implications for the way we do things. And in order to kind of take you into that a little bit, I'm going to do a very simple exercise where we say, okay, if we think that non-blocking and asynchronous is important, how do we actually do that in Java? Let's see where that takes us. So we have a user repository, and that has typical methods like, for example, finding a user. And if we can't find that user, there will be an exception. This is what I mean by imperative programming. It's a bit of a fancy word for basically laying out your logic in a straightforward top-down fashion, where you say, call the user repository, find me a user, and then when that user is there, I continue to the next thing. Or maybe there is an exception, and then I deal with the exception. And if you have a stack trace, something wrong happens with the exception, you can see exactly everything, because imperative logic means that before you can continue, you got to wait. So the stack trace basically shows you exactly where you are and what's happening. It's a single thread. Now, if we want to make that asynchronous, first of all, there's no guarantee that the exception will happen on the same thread. Asynchronous means that the result will be ready later on, and it may come back on a different thread. So here we have a future, and the result may, if the underlying repository is really non-blocking, it may actually exit the thread completely and then tell us when the result is ready, notify us, which means that instead of a result, the actual result may be an exception. So that's why we can no longer declare an exception. It's not reliable that we're going to get it in the same thread. But if you actually want to go this route, this is really actually a blocking approach, because if you have more than one future, for example, you're calling different services, and the first one depends on the second one, how do you actually get the result from the first one? You have to say future.get, which blocks until it's ready. So pretty soon you're actually back into blocking mode, and then you have all these exceptions you have to deal with. Java futures before Java 8 are basically blocking. But in Java 8, we have completable future, which is a major improvement over future with some good ideas and essential features. So a completable future actually adds a new concept, and that concept is callbacks, declarative style callbacks even better, which basically means that you, instead of calling future.get, you say, this is what should happen when the result is ready. You're declaring what should happen next. So now we're getting into a more declarative style mode of asynchronous logic. This is very different from imperative logic. As you can see, we're beginning to split out the logic into chunks, and we're declaring what should happen next. It's the same logic, but we're splitting it out and laying it out differently. And the code is becoming kind of more neutral to asynchronicity. Like this may happen in the same thread or not. It may happen it may switch threads. So that's good. We can do it like that. But what do we do with find all? So we can say completable future with a list of users. Maybe that works. For the save method, I'll come back to it in a second. For the save method, we're going to have a completable future of void. And that may look strange. Why are we doing that? Why can't it just be void? Well, this method is asynchronous. So when we call save, we don't know when the save completes or if it completes. So that's why we have a completable future of void, because there is no return value, but we do need to know when it's complete, and we do need to know if there was an exception. So that's basically the notification mechanism coming back to us. And if it looks like a scary new world, well, asynchronous programming is not easier. I'm not promising that. And we'll come back to the question of when do you do that and should you do that. But these are topics that we need to get into. So completable future is fundamentally the right idea for use in async APIs. It has declarative composition of async logic, means that your callbacks are, it gives you a nice mechanism for declaring You're not nesting your callbacks all the time, but you can just keep declaring what should happen next. And the lambdas keep it very, very readable. The problem with completable future is that it's not ideal for dealing with more than one value. For collection return values, that's where it begins to fall apart. It's really not built for that. And kind of a variation on that is it doesn't really deal with latency sensitive data sets. So if you have something which, if you have a collection, it's more or less somewhat possible fit, but if you have data which keeps coming, maybe not at the same time, one, then a few seconds later another one, those scenarios can happen in stock ticks, events of all kinds, messages. Again, completable future in collection is just a no-go. Also, no way to represent very large or infinite data sets. So ultimately not a perfect solution. So back to the drawing board. What if we think about all async return values as just a stream of notifications? It looks like this. You get a notification for each next item. Here's another one, here's another one, here's another one. That may be one, or it could be many. It doesn't matter. And at some point, you may get an error or completion notification to tell you that no more values are coming or there was an error. And if you think about that approach, that actually allows you to represent all the possible combinations, all the scenarios. Here you see on the left all the return types, void, user, or previously in a blocking imperative API, a list of users. And then there are different scenarios for each one of these. You can have success or failure. You can have match, no match. You can see on the right that we can uniformly represent this with callbacks. For example, a save has an on complete or on error. When we're looking for a user, we're getting on complete immediately, which means no match, no user, just a complete notification. Or we can get one or more users. So basically, we can represent all of this as a stream. Now, we actually have a stream API in Java. That's the Java 8 stream. For those of you who have looked at it, it's a bit like the completable future. It has a very nice declarative API. Lambdas make it readable. But again, it's built for collections. The stream API is for collections. That's kind of solves a specific problem, but it doesn't solve what we need here generally. It's not for any kind of active or hot source of data. Again, if you have things that aren't, what the stream does is it's a pull-based mechanism. It says, give me the next item. If all the items are there, that's good. You just keep getting the items it's processing. But if the items are not there, if there's any kind of delay or any kind of hot source that actually needs to push the data as it becomes available, now suddenly you find yourself blocking, because you're trying to pull for something that is not there yet. Of course, it can be made non-blocking, but anyway, Java 8 Stream is really built with collection semantics and for collections. So these are actually not my words. Doug Lee, who is the lead for the concurrency module in Java 8, these are his words, or kind of an abbreviated version, for why the reactive streams specification is being added to Java 9. He's basically pointing out that until now, in Java, we have a missing category for these kinds of push-style operations that as they become available from an active source. What is the reactive streams? Well, that's an interesting example, actually, of a collaboration among several industry vendors, companies. Not part of any specification process. They just come together and create something useful. In fact, so useful that JDK decides to include it in the JDK, a kind of organic effort. And that includes companies like Netflix, Kazing, TypeSafe, now Lightbend, Pivotal. We have also the leads of Project Reactor participating. And it's a very small spec, just 4 interfaces that define a publish-subscribe relationship. It's meant to be an interoperability spec, so components that want to be non-blocking and asynchronous can talk to each other. And the key concept there is back pressure, which means that a downstream component can tell the upstream component when to publish more data, when to give me more data. If you think about, let's say, a non-blocking database driver, and then a web application, and then an HTTP client, if you set it all up with reactive streams, then basically if you have a slow HTTP client, wouldn't it be nice if you could send signals upstream to say, I can't write right now, I'm blocked, the client is too slow, so then the database component doesn't have to send any more data. So that's kind of what this is really about, what it's trying to set up. So we have Project Reactor at Pivotal, and that's built on reactive streams, and it's also with RxJava and ReactiveX in mind. It's kind of bringing these two concepts together. This is where, if the Java language doesn't give us enough, one strength in Java is that we have a lot of libraries and people can provide what's missing. And this is exactly what RxJava and Reactor are doing. There's others like Akka Streams and there are other efforts also that are picking up reactive streams, the specification. And it's nice because you can, begin to do things with that. And Reactor, of course, gives you that same composability like the Java 8 Stream API. So it's basically dealing with any source. It can be a collection, it can be a hot source, it can be an active source, it can be a cold source. It can represent, it can be used for non-blocking APIs. And this is what it looks like. We now have a user repository where the find by ID returns a mono. The find all returns a flux or a mono void for the save method. And we'll dive more into that in the next session, and we'll see how this is supported and used in the Spring Framework. But I just wanted to go through this kind of a little tour of what's available in Java if we want to start going down the asynchronous non-blocking route and where we actually end up, once we go down that path. So you can kind of see the general goal to become non-blocking, to become more resource efficient, kind of Node.js style event loop without blocking anything. There's definitely a cost associated with doing that, and we'll talk about all these things in the next session. But let's take a break. If you have any questions, you can keep those, and then we should have more time after the next session to cover those. Thanks. I won't repeat much of what I said, although it's on the same topic, the same goal. And if some of you are just coming for the second session, then this can also serve as a quick introduction. So what reactive programming is, it's a style of microarchitecture. It's a way of writing applications where instead of doing things the imperative way, the way you lay out the logic is much more declarative, functional style composition of logic. Because when you want to be non-blocking, then you kind of have to do things in this way to become neutral to asynchronicity. So here's an example of imperative blocking logic. I mean, this is basically how we, by and large, we write applications today. You have a user repository with methods, and then you use that, and you wait for the results. So if there's any kind of blocking involved, you're holding a thread, and that's using a certain amount of memory because you're down the stack, and at each level of the stack there's some variables. So there's a cost basically associated with this, and with functional, with kind of reactive programming, you're using something that looks more like this, where your repository, and I'll talk about this as an example with using Reactor. The Reactor library is similar to RxJava. But you basically get the results back from the repository, and then you declare what to do after that. In this case, we're filtering which users, then we're mapping the user, and logging, and there are other operators that we can apply. But the point is that this logic is now neutral to asynchronicity. There's nothing in there which assumes that by the time we find all returns to us, that's going to happen in the same thread. We may, in fact, exit the current thread and then receive a notification back from another thread, and that's when the filter continues. The logic is laid out in such a way that there is no assumption anymore. It's broken down into smaller chunks. And also, until you call subscribe, nothing ever happens. So that's one big difference, again, between imperative and reactive programming, is that you're now declaring the logic, but nothing is executing, nothing is actually happening. We're not hitting a database of any kind until there is a subscriber at the end. So there's kind of an initial phase when you declare, you make a pass-through. So let's look, actually, another way to look at reactive programming, and actually one of the main reasons why we're even started thinking about it 2 years ago, is the impact on runtime. How does this look from runtime perspective of runtime characteristics? So this is the typical model that we're used to today with the servlet container, where we have a thread pool, and for the servlet container has a thread pool, and we get a thread allocated for each incoming request, and then we handle the request, and when we're done, that's when the thread is released back to the container. And of course, each thread can take a certain amount of time to do things, and over time the things we do are more asynchronous themselves and they involve latency. So we use thread pools as well, which means that there's network latency involved as we make calls out to other services. And the other thing to keep in mind is that with web clients, when we write back the response, we're also exposed to whatever clients are connecting to us. They may be very fast or they may be very slow. And if you have a lot of slow clients, that will begin to fill up your thread pool, because it's not only about the application being blocking or non-blocking, it's also how the servlet container exposes I/O. So when we are writing the response back to the client, the JSON or whatever it may be, if that blocks, again, we're blocking a thread that's part of the servlet container pool. So you can see those numbers on the left. These are the milliseconds. Those numbers are out of your control. They may go up, they may go down. They may be more, they may be less, they may be flaky Wi-Fi clients. There are all kinds of ways in which your thread pool may be exhausted very quickly. And it's very difficult to configure in a way that is resilient, because there is no predictability there. You're basically at the mercy of who is connecting and how many are connecting. So ultimately, this can scale, and as you know, we tend to scale horizontally. When one JVM kind of reaches its limit, then we have a load balancer. We have more than one, and then we can service more requests. And we're here today, right? We're alive. Applications are working. It doesn't mean that it can be done. In fact, it can be done quite effectively, very clearly. But more and more, some applications are finding that this is inadequate, and that's where we begin to discuss trade-offs a little bit, because what we're proposing here with reactive programming doesn't necessarily mean that all of this is bad. It's just about providing choice. It's about having another option in the portfolio. And as you can see, we go through a lot of effort to make sure that the programming models are as consistent as possible, so that no matter which side you're on, and you may choose to do some applications in a microservice architecture, one microservice can be kind of more blocking style, imperative. Another one might be more functional, reactive. But we're trying to keep things consistent and provide choice, rather than say, this is how you should do things now, and that's old, and you should put that behind. That's not at all what we're doing here. We're just naturally evolving, providing choice, and that choice is for you. Now let's look at the alternative of this. From a runtime perspective, we can also talk about event loop style processing. And this is what Node.js really kind of pushed to the extreme, in a sense, because they were constrained, again, with a single thread. But this is the idea. We have, in this case, of course, on the JVM, we can have more than one thread, typically trying to aim for number of cores on a CPU, on a computer. In this case, we have 3 worker threads, and the important thing is that that's all we have. We're not going to allow a thread pool that can grow any more than that. So it's just 3 threads. And the way that they work is when there are requests coming in, non-blocking I/O that's available in Java basically means that what the server can do is it can check for each incoming connection. Is this connection capable of reading or writing at the moment? Yes. Then let's start reading or let's start writing. And then when that answer becomes no, we move on to the next connection. So you can imagine that we can now go in this kind of round-robin fashion and keep doing things, keep busy, keep the CPU busy where we can. And that becomes a very effective way to deal with a lot of connections without allocating a thread until that connection is done doing what it's doing. So it's basically a different way to handle requests. Of course, so it starts with the runtime. So you have a non-blocking runtime. And probably many of you have heard of Netty. So Netty is a very popular choice for non-blocking runtimes. And that's something that we're supporting in Spring 5 already in our integration tests. But I should point out that Tomcat and Jetty are equally capable of doing that. They're, in fact, underneath, they're using non-blocking I/O. They're using event loop style to deal with connections. But then you have the servlet API on top, and by the time you consume this through the servlet API, that servlet API is blocking. So you're now in a model where you must process each request in its own thread. So really, it's not the problem that Tomcat and Jetty cannot do this. It's just that the way it's the servlet API model that's kind of mandating that it's done in this way. And if you go back to the beginning when servlet API was first created in 1997, approximately, relative to CGI, that was a big improvement, right? In CGI, you have one process per request, and then we said, well, in Java, we can do one thread per request, and that's much better and more efficient. And it's a model we adopted, and it's a model we still use, but so many things have changed in those 20 years since then, almost 20 years. But yet, we still use the same execution model. So that's really kind of where this goes back. We never had a strong reason to go back and change things very. So there's a lot of inertia, but now you will see more options along these lines. Now, applications must also become non-blocking, because if you block, you can be a little bit blocking. That's not allowed, right? You can't cheat. Like previously, we would say, okay, if a particular call to a database is slow, we might put it in a thread pool, make it asynchronous, and we'll deal with it that way on a case-by-case basis. Now you have to become fundamentally non-blocking. You can be a little bit non-blocking because you have only three threads in our example here. If you block, very soon your server will be locked up. So the assumption here is that we're no longer blocking, and when we're not blocking, we're writing applications, we must deal with callbacks. So if you imagine the algorithm for preparing rice, you will add the water, but then you don't really want to wait until that boils, so you get a callback. And when that's the case, then you can lower the heat, and then after that you get another callback. So you get the point. If you're dealing with asynchronicity, everything becomes a callback that may be potentially blocking. And now pretty soon you find yourself nested many, many times to the right. And that's called callback hell for good reason. And there is another way to do this. Basically, if you want to achieve a kind of harmony with callbacks in asynchronous world, you have to kind of be a level above that. And that's where we talk about the declarative style programming model. And ReactiveX and RxJava kind of popularized this. Of course, I talked about Java 8 Stream earlier. It's very similar. But ReactiveX and RxJava kind of take that further, because it's not only for collections, it's for any source of data. It's dealing with any kind of sequence of data. You have the concept of time. You can apply time-related scheduling. You have the concept of timeouts. Those are things that are not in the Java 8 Stream API. And also, again, they can easily represent collections, but they can also represent hot sources where information may come now or it may come later, and you don't have to hold a thread for that. Now, interestingly, ReactiveX is actually a broader umbrella of technologies. It originated at Microsoft with Eric Meyer. Kind of more of a UI bias there, or origins for dealing reactively with events that are happening, like mouse movements, etc., and applying then these kinds of operations to deal with what to do next, laying out your logic. But due to all the things I've talked about so far, this has become a hot topic in writing regular enterprise applications, everyday applications. So it becomes an interesting paradigm for dealing with callbacks. Instead of callbacks, you kind of have a more declarative way of doing things. So RxJava became 1.0 a couple of years ago, 2014. A lot of articles out there, and it served as a good model. Also, in the meantime, just a little bit after RxJava, maybe by half a year, we have the Reactive Streams specification, which again was a collaborative effort. A number of companies just kind of came together and put together a very small spec just for interfaces. It's focused on interoperability and the concept of back pressure. The idea is that if you have a publisher and a subscriber, an upstream and a downstream, kind of a data pipeline where something is producing something and something is consuming it, it shouldn't overwhelm the consumer. The consumer should be able to say, I don't want any more, pause or stop. And when I first looked at reactive streams and back pressure, I tried to relate to examples of sources that cannot slow down. There are things that cannot be slowed down. You cannot say, give me less. It cannot give you less because, say, stock prices or mouse movements even, you can't stop. Those things are happening. They're coming at you, whether you can deal with it or not. So I couldn't understand, well, what do you do about that? So the point of reactive streams and back pressure is not to say that there's some kind of magic way to slow these things down. Still, in those kinds of situations, you will have to somehow either drop or buffer, or you're going to have to apply some strategy to deal with the overflow. But the point is that there are many sources which can be slowed down, and if you put a kind of contract at the boundaries of components that says you cannot give me more than I said you should give me, then it becomes the responsibility of each one of those components to deal with what should happen. So that's kind of the idea, is to set up a world in which components can communicate this information, and then if they can actually slow down, they will. If not, they're going to have to deal with what to do otherwise. And the downstream component also has a choice to say, well, keep giving me and then I'll deal with the overflow myself. So it kind of sets up a situation where you can still allow more things to come. It's just there's a control mechanism. These are the contracts in reactive streams. It's kind of nice that you can put the whole spec on one slide. Technically, there's one more interface, which is a combination of publisher and subscriber, but these are the key ones. So you have a publisher and you have a subscriber, and there's nothing revolutionary there. I mean, that's a thing we've had forever. The thing which is new is the subscription, which the subscriber gets at the time of subscribing to the publisher. And you can think of that as the volume knob. You can see it at the bottom, which gives you a request and a cancel. And you can say, give me n number of items, or at some point you may decide to cancel. And what n means is really kind of left opaque. It's just a mechanism that says, give me 5 more, and then after those 5 you can request more, and if those 5 came too fast, you can say, give me 1 more. You can kind of slow down like that. But it's not meant to represent like a byte count, or it's intentionally left as kind of something that's very opaque between publisher and subscriber, and the libraries can implement different ways to actually deal with back pressure, different strategies. Again, this is low-level stuff, but it is an important mechanism to understand, which is why I'm presenting it here. Then we have Project Reactor. Again, when we started 2 years ago, it looked like RxJava was the answer. And it certainly brought a lot of good ideas, but we also worked very closely with Project Reactor to experiment with these ideas. And the advantage of Project Reactor was that it came on the heels of ReactiveX and Reactive Streams, and was able to kind of put together something which borrows ideas. Well, it's actually based on Reactive Streams 100%, which RxJava was not, even though they participated in the spec and they have a bridge. But also have the same kind of patterns that are available in ReactiveX and RxJava. So if you're familiar with RxJava, then using Reactor is going to be a very straightforward thing. There's a great deal of consistency and even collaboration between the projects. So we're very happy actually with where Reactor has come. It's at version 3 now. The first 2 versions, you can think of them as more experimental when things were happening. Version 3 is the real deal. That's a core dependency for Spring Framework. We worked hard for a year and a half with the Reactive team, kind of going through the stuff that we're doing and kind of raising questions and requirements and making changes. Also, for those of you who may be familiar with the Java Cloud Foundry client, that was also rewritten to use non-blocking style reactive programming, and because there were a lot of HTTP requests that the Cloud Foundry API exposes in its REST API, so they found a lot of benefit in actually using non-blocking approach to combining those into more cohesive, higher level operations. A lot of benefit in doing that the reactive way. And they also work closely with Reactor, and we think Reactor is actually kind of a leader in this space now. And we think that train is going to continue because, first of all, because it's kind of more catering to enterprise applications. It's us imposing the requirements, or rather stating requirements and making sure that we have answers. It's also, it has the ability to deviate where it needs to from ReactiveX as opposed to having to stick to ReactiveX, which is kind of implemented in other languages as well. So that freedom is actually quite nice. And it's going to continue to work like that. I mean, as more Spring projects like Spring Cloud Stream and others, Spring Data, are working with Reactor, all these angles, all these things that we do in enterprise applications are practically defining their requirements. I think in that sense, RxJava has kind of a different audience. It's largely a lot of Android actually use, which is why they're sticking to Java 6 even in their version 2. So you can see there that there's quite a difference, which is subtle, but actually it has quite a bit of implication for the end result. Again, we're very happy with Reactor, very closely aligned with RxJava, but much more along the lines of what we need. So there are 2 types, Reactor Mono and Reactor Flux. They represent a stream of one versus a stream of many items. We found there are schools of thoughts that basically say that there should be just one type, Flux, because any stream can be represented. But we found that in APIs, especially if you look at the user repository, it's quite nice for an API to represent the differences. How can you say find user is an observable or a flux or a stream? It's just one item. It's always going to be one item or 0 items. So it's quite nice to have a dedicated type for doing things like that, and it's something that we found very helpful in our framework kind of functionality dealing with applications. And then this is an example of a marble diagram. You can see at the top a sequence, time-based sequence where items are coming in. And then there is some kind of an operator, like a filter or map, that's going to do something to each one of those items. And then you have a new resulting flux at the bottom. And you can have many of those stages. You kind of declare a pipeline of what should happen with the data in each stage, each phase. So basically, it takes time to get used to and to learn, but eventually you get the concept that you represent everything as a stream of notifications, and then you have all these operators to deal with what to do with that data further, and it's kind of a general purpose reactive programming API for your logic. So here's a reactive repository once again, using the non-blocking types, and we can work with that. We can then do all kinds of operations. And here it may seem a lot like dealing with a collection. Like you might say, okay, I don't write code like that. I do much more general purpose things. Trust me, I mean, this is actually you can do general purpose algorithms here, not just dealing with collections. Very much the idea. In fact, we went through that in Spring MVC, and we had to replicate a lot of the logic, the entire logic of the Spring MVC framework in reactive style, bound to non-blocking contracts. So here's some example output, and what you'll see here from the log operator, the actual reactive streams contract in action. First you have a subscribe. Until there is a subscribe, there's nothing happening, right? If I stop at the log and exit, nothing will happen. So I have to have a subscriber. And then the subscriber will make a request. By default, based on this example, it will request all the data. That's a long max value. Is the special signal there. And then we get as many users as there are, followed by onComplete. Now, in a lot of cases, you're actually not going to deal with back pressure very explicitly. It's a cool concept, but it is more for the frameworks to deal with. So if you have a database component and then a web framework again in an HTTP runtime, the database component and the HTTP runtime should deal with back pressure to each other. But in the middle, you're just doing stuff and you're dealing with the data, declaring what should happen with each item of data. But you're not necessarily explicitly managing the back pressure at that point. So typically that's not something you explicitly deal with. But just for the sake of an example, if we insert this capacity operator, then the output would look more like this. You have a subscribe, and then you have request for 2, then 2 more, and then 2 more again. So you may be thinking, well, what's the big deal? I got them all in one, or I'm getting them 2 at a time. If it's all happening in one thread, you're right. This seems like a silly game that you just say, give me 2 more. But again, remember that this is neutral to asynchronicity. Imagine this happening in multiple threads. Let's say that our repository was truly non-blocking, and what can happen here is that when you say give me 2, it comes in a thread. Let's say they're available immediately, gives you 2 users, and then you don't request anymore, and then it exits, and we're not using any thread, right? It's just waiting. There's just a something will have to trigger the subsequent request. Maybe we got a response back from another service, microservice, and then we said, oh, now give me 2 more. And now it comes back and gives you 2 more. So you can see how this can really work, actually, when you have multiple threads in action, and you're not actually occupying threads. This can take much longer. So let's talk about the Spring 5. Turn to Spring 5 now. One of the first things, this is not technically Spring 5, but since we're talking about repositories, it's worth noting that Spring Data, the Spring Data project, is also working on reactive support. So for example, the way you know that you can declare an interface and then Spring Data will automatically implement that interface against your persistence layer, persistence provider. The same mechanism you can use to implement, you can see here we just have the reactive return types. And the same can be done with RxJava as well, so you can use observable as the return type, and it will work as well. Currently, Spring Data is snapshots. I don't think they have a milestone yet. They're aiming also for early next year, Q1, I think, for a release. But that's in the works, and that's important. At the moment, this can be done against Mongo, Couchbase, and they're working on Redis as well, because those are providers that actually have non-blocking drivers and reactive drivers. So wherever possible, they're adapting that too. But this is pretty cool, because in case you're wondering how am I going to implement this repository, Spring Data will do it for you wherever it's possible. So now what we really want is to end up with a situation where we have back-to-back end-to-end back pressure. We have different components here, and it's a kind of pipeline that we set up. So in Spring 5, first of all, we now have support for all of this all the way down to the runtime. But as you go up to the controller level, what we figured is that actually the controller programming model isn't blocking in any way. It's just flexible method signatures. And here's an example of something we support in Spring 5, where you have a get user, get users. So you just take those repository methods, and now you can extend that through a controller, just return those values, and your runtime, your framework underneath is completely non-blocking. Now, underneath this is actually not Spring MVC. It looks like Spring MVC, but it's actually another module called Spring Web Reactive, which doesn't physically share any code with Spring MVC, but it shares a lot of the algorithms. They're just rewritten around non-blocking contracts. And also we're adapting down to reactive streams to different runtimes. Now, you may wonder, why don't we do that on what's the difference with Spring MVC? Like it looks the same and you have flexible method signatures, but if you think about what it means to return a flux, in Spring MVC with the servlet API, in order to write the flux, you have to start calling the servlet output stream, and that's a blocking call. So if we take and start writing the first user, we now are blocking, and let's say after the first user, we can say we can break it up into one user at a time. So we can say, okay, until the next user. But what do you do until the next user? Do you exit the servlet thread and then continue when you have another user on the flux? It's just, again, the blocking approach cannot be done piecemeal. Servlet 3.1 gives you non-blocking I/O, and we are using it. But we can't use it in Spring MVC because you can't just introduce it in an ecosystem where everything else is blocking. All the other libraries are blocking. You kind of need to go all the way. So this looks the same, but underneath is a completely different foundation. And we adapt pretty well to RxJava as well. So we support that easily as a first-class citizen. Again, you saw this diagram earlier, I think. Basically, we still have the Spring MVC support on the left-hand side that's going through the servlet API down to any servlet container. And on top, we support the annotated controllers. And on the right, you see our new runtime stack, which is we support Tomcat, Jetty, will adapt to any servlet 3.1 container. And that's important because the way we adapt is through the servlet 3.1 non-blocking I/O. So there's actually a way to go to the input and output stream in servlet 3.1. It's a little funny they kept them as input and output stream, which are kind of symbols of blocking. But anyway, the servlet input and output stream, they do give you mechanisms to say, can I write? Is it okay to write? And if the answer is no, they'll call you back in another thread that says, now you can write. So those things are there, but they're not easy to use in existing applications. But that's the mechanism we're using. So we're adapting that to reactive streams, back pressure, contracts. And the very nice thing, very cool, is that we also support Netty and Undertow. These are non-servlet containers. So that shows you the strength of this approach as well, that we have a new kind of abstraction which doesn't depend on the servlet API, and that solves a problem that we've been hearing for some time where people say, I'd love to run Spring MVC on Netty. How do I do that? Well, now there's an answer, and now there's a natural way to do it without any compromise, kind of done all the way. Then on top of that, we have a reactive HTTP layer that is a common layer for doing things, kind of a reactive streams / HTTP abstraction where we're adapting to all these different runtimes. And then on top of that, we have Spring Web Reactive that, for example, enables the annotated controller model and also the router functional style, Lambda style routing of requests. Did I go? Oh, I went the other way. Okay. So just to give you a hint, I don't want to get too much into that detail, what the underlying foundation includes, but we have a reactive HTTP kind of adaptation layer where instead of getting input and output stream from the request and response, the request and response are actually giving you a flux of data buffers, and also you can publish with data buffers. Again, this may look scary, but you're not dealing with that. This is just to show you that at the core, this is adapting to reactive streams with back pressure, and then we have more facilities on top of that, but we are adapting this to all the runtimes that I listed here. And then on top of that, we have a serialization mechanism that you can go to JSON, and you can go to XML, you can do server-sent events, all of this on top of that reactive streams foundation. These are all new contracts that are essentially reactive and non-blocking. The interesting thing with JSON is that the Jackson library itself is blocking. So if you're parsing an incoming stream, the way we solve that one for the time being is by actually parsing ourselves the stream and then if you have an array of objects, we're actually pre-parsing individual objects so we can feed them one at a time to Jackson, so that by the time we give it one object, that's already, we have all the data, so it doesn't have to block. But the Jackson library in 2.9, we're hoping, we've been in touch with the developers that they may actually provide a non-blocking parser, asynchronous parser. And then on top of that is the Spring Web Reactive module. So this is parallel to Spring MVC, kind of does a lot of the same things, a lot of the same algorithms. In fact, in many cases, we had to literally take, what it does over there and then put it over here and make it comply with new contracts. That's what it came down to. We can't use the servlet API, so it really goes all the way down. It's using the reactive encoders and so on. But the good thing is that actually the two are sharing a lot of algorithms and mechanisms. The way you do content negotiation, the way you do, the way you deal with all the annotations that we have, the way you do validation. These things don't change. They're still the same. We're just changing, the I/O aspects, the way you read and write. If you're kind of feeling on one side and say left out from the other side, that's not the case. We're actually supporting both of these approaches. As issues get open on one side and requests or on the other side, each side benefits because when we fix something on the reactive side, we're also going to fix it on the servlet side. Or if you're working on the servlet side, that's benefiting the reactive side because we're keeping those consistent with each other. They're not completely disconnected. An example of a non-blocking HTTP GET. You can see two different ways. If the first method signature looks kind of blocking, it's synchronous for sure, because if I'm returning a user, that means I have to produce the user before the method can return. So that's kind of a signal for synchronicity already in the method signature. But in this case, we're just creating the user. There's no non-blocking, there's no blocking of any kind, so why not? We can support this kind of method signature. It's not a problem. But you can't call something that's going to block to give you back a user, because then you'll now be locking one of the very few threads. That's kind of an implicit assumption now. You can't block inside your controller methods. And then the second method shows a more common, more likely scenario where you're actually calling something that's giving you back, say, a mono or flux or RxJava observable and so on. And also on the input side, if you have a HTTP post, we can take a user or a mono of user. Actually, the first method implies that possibly over multiple threads, we've read all the input from the client without blocking, turn it into JSON or whatever, from JSON into a user, and only then call the controller method. Right? That's what the non-blocking actually means. For the second method, we can call as soon as we don't have to wait until the entire input has been received, because we're giving you a mono and then you declare what should happen after that. So there's kind of a slight difference here, but we support both of these method signatures just the same, and they're non-blocking, each of them. Server sent events is probably the only way you can do kind of natural streaming into the browser. Of course, if you're not in a browser, then you can return a flux of anything, and then if you're reading with a Java client, that's going to just give you things one at a time. But into a browser, you actually can't make use of streaming very easily. With server-sent events, the browser actually will give you things as they arrive. That's why SSE was built. But otherwise, the server is very efficient in streaming, but the client won't see anything until the whole thing arrives, because that's how AJAX works. We support something called zero-copy file transfer. This is basically on the level of non-blocking I/O, handing a file handle to the runtime, and then the runtime efficiently transferring those bytes without minimizing copying, in-memory copying. So all those things are performance characteristics. We have a web client, which is an alternative to the REST template. You can see that we've gone for more of a mock MVC style API here, but it's, again, fully non-blocking. Currently, it supports RxJava as well, already. You can do scatter gather. So this is where things begin to become more interesting because that's an example of a method where first we're calling a repository to obtain an account which may be blocking. And then once that account is there, then we turn around and call another service which also may be blocking to obtain additional information, maybe account alerts from a different system. Trying to do this asynchronously with futures, you kind of have to set them up one after another. They're dependent in that order. But here, that syntax may be looking like, okay, how do I actually begin to parse that? But you can still see kind of generally what's happening. The declaration of it is there. It certainly takes a little bit of getting used to what is flat map and all that. But the point is that you can set up these things quite easily, and they're non-blocking. In terms of threads, what can happen here is that the repository may find an account, and that may not be immediately, calls you back in a thread. Now, when that happens, then you make a call to the next system for the alerts, and if that's a blocking call, you may exit the thread, and that will call you back. So these things now automatically happen. You have a way to declare them. We also have a functional web framework. I'm speeding up a little bit here, but we're almost at the end. So that's an alternative. That whole functional model is already creeping into the annotation side as well. You can see here the use of Flux pretty much implies that what you do inside the controller is actually very declarative. You're already in a very functional style world. So, this is a kind of an interesting complement. It's an interesting alternative that makes sense now that we're Java 8 plus in Spring Framework 5 to provide this alternative. It's very transparent. It's very, there's no annotations, there's no reflection. It's very minimal, very transparent. It's like 10 classes maybe on top of the reactive foundation that we already have in HTTP. You can see we're building the routes here. We're saying route this or that. The handling is right there. And then we're simply turning that into an HTTP handler and passing it to get the server started. It's kind of cool that you can fit the whole thing on a slide, I think. But it's also very, very transparent. I mean, you're calling everything yourself here directly. It may not be something that everybody does. Again, I don't mean to present that as, this is the new way and that's the old way. But this is definitely something that makes sense. When Lambda's Java 8 is available, we're experimenting with a new way of doing things, and we'll see where that takes us. Certainly with the method references, it looks quite attractive. And if you want to give this a try, probably the fastest way to do it right now is to go on Start Spring.io and just make sure you pick Spring Boot 1.4 at least. It's actually not in Spring Boot 1.4, but you have to pick that as a minimum in order to get this option. Then you type Reactive and you'll see this. So that's how you can give it a try. The Spring Boot Reactive Web Starter is experimental. I mean, obviously Spring 5 is not there yet, but it gives you an opportunity to try it. And this is the source for the Reactive Starter for the moment. There are some useful instructions there, so it's worth checking out that link as well. There's also a way to do it with just a few lines of code. If you check out the Spring Framework 5 snapshot reference, you will find it's really quite trivial to start by hand as well. So that's the end of my talk. I think we're just at the end of the time, but I can take a few questions. Is there any? Between what?
The two approaches you mentioned. So you say you have the reactive model, you have the non-reactive model. You say even if there is the reactive model, you should not discount the other model.
Oh, the pluses and the minuses between the different models. So there's first of all the annotation-based approaches, which can be done the reactive style or the servlet, traditional servlet Spring MVC. And then on the reactive side, you also have the functional. So there's actually 3 choices there. There's actually an interesting blog post on the Netflix tech blog. Last week, I think they posted it, where they talked about the their own experience of rewriting their gateway. That's all the requests coming through there, from blocking, actually servlet blocking, to non-blocking with Netty. And they give very honest assessment. It's kind of interesting. I mean, I read it, and for me it was like, yep. That's kind of the things we've been going through over the past 2 years. But it's interesting to hear it from Netflix and in their words and their actual experience. And you can see a little bit of the pain there as well, because with the non-blocking, they're very honest about explicitly saying that the difference between the imperative, where you get a nice stack trace that tells you exactly where things went wrong. Now you're in a world of callbacks, and even though this declarative looks nice in the source code, underneath there's still callbacks. They're just connected in a nicer way from a programming model perspective. So debugging experience is much harder. Even writing code, it's a big adjustment to get used to. I read it from other people who said, don't feel stupid because it takes a while to get used to this, and then I felt stupid. I went through that same path. It really is like that. It's a different way of doing things. It's almost like learning to walk, and it's frustrating. You can't do anything about it. But it gets better, and then you learn, and so we'll see over time just how much it takes over. But I think for now, it's kind of driven by two factors. First of all, are you already experiencing runtime issues that are really making you think, I could save a lot of money, if I could just have a more efficient resource footprint? If you're already finding yourself thinking about that, then you probably should look at this. If not, then you can experiment, but I wouldn't recommend doing it today. Also, it's going to depend on the use case and whether you can go all the way non-blocking. If you are using actually some blocking libraries, if you must at the end of the day call some blocking libraries, you will not get the same benefits. There are ways within Flux and Observable to actually put things on a different thread for the remaining part of the pipeline. So you can basically fall back on a thread pool approach as well. But again, you're suffering the pain, but you're not getting the gain. So it's a bit of a trade-off like that. You have to think about those things.
How do you know that the library that you're using is blocking?
Can you ask your question again?
How do you know whether the libraries that you're using is blocking or not?
Okay, how do you know if it's blocking? If it's doing things like input stream read, output stream write, if you have an SSD drive, that's going to come back very fast, so you probably won't know the difference. But if it is a network drive, or if it is even not an SSD, there can be quite a delay, latency. If you're doing HTTP calls out to another service, there's no guarantee when that's going to come back. So if the HTTP client you're using is blocking, then that's a blocking call. In that same blog post I mentioned, they reference something called Reactive Audit. It's like an open source tool that's using AspectJ. You don't have to touch any of your source code. It will actually, at runtime, as you exercise the code, it will tell you when blocking calls are being made. They said it was very useful to them. So, but conceptually, you get what I'm talking about.
Okay, is it a quick question? Yes. Fast question.
First casualty.
Good save, by the way. Good save.
So my take is all along what I was listening is my background is more on the message-based programming.
Okay.
And my day in, day out, I am asynchronous, like publish, subscribe, and all those stuff. So I think that the underlying product is still a blocking APIs. So do you think that now those message-based products like TIBCO or web methods or these things, they're going to rewrite their programs or rewrite their engines for these things? Because now my license is based on threads. So I buy a product, it is like 10,000 threads. And then all they are using is underlining is the block threads. Then that's, I am unnecessarily paying them 10,000 threads license, where they can rewrite it to 1,000 threads. I can buy 1,000 threads. So
certainly there's a conflict of interest there.
Yeah.
Well, I think probably, I think You know, it's a question about transition as well, and it's also about understanding properly what asynchronous is versus non-blocking. Some things can be made asynchronous by putting them in a thread, but the underlying thing may still be blocking. So generally, if you're using a thread pool, you know, for calling something, you can make it look asynchronous, but it's still underneath it's blocking, and there's a cost associated. Your memory grows, and you can only handle so much. 10,000 seems like a large limit, but actually when you remove those constraints, that becomes pretty natural. You can go much higher than that, right? Because the cost is much smaller. Now, again, you know, we are providing a web framework, which I think is already pretty big deal, because most applications start from there. That's where Spring Framework also started from, with web functionality and then other things around it as well. So it's pretty fundamental to most applications. Web applications are by nature very concurrent. It's a little different from messaging applications, let's say, but that high degree of concurrency means that there's a good chance that there's a big benefit to be gained from that model. It's very different from a big data application, which is just continuous stream of one thing passing through. So I think that's a huge jump start, and Spring Data is already, you know, working, and there are some drivers. I don't think everybody's going to turn around. It's going to take a lot of education, you know, for all the providers as well. But ultimately, this is happening not because somebody thought it was cool, like SOA, you know, but it's happening because there's a real thing, underlying benefit to it. And as I said, I mean, we started 2 years ago, not because we thought it was cool, but because companies were trying to do that, and they weren't finding solutions. So from our perspective, we actually really like the approach of giving choice. Because we really don't think this is going to be for even a majority of applications. I think this is still a minority of applications, but it's a very important choice. It needs to be there in your arsenal so that you use it when it's the right answer.
Okay.
So hopefully that creates momentum, but beyond that, I can't really say.
Awesome. Thank you, Rossen.
Thank you. Thank you.
Okay, so everyone grab lunch as quick as possible, and Chris is going to give us a demo once everyone is somewhat settled of Spring Tool Suite.